Thank you for joining us on Synthesis Workshop. On today's Research Spotlight episode, I'm very glad to be joined once again by Craig Day. Craig previously joined us in episode 52 to talk about his mechanistic work on nickel-catalyzed Negishi couplings, and today he'll be telling us about new mechanistic work with a different transition metal. To briefly reintroduce Craig, he did his master's work at the University of Ottawa under the supervision of Darren Fogg, and is currently a PhD student at ICIQ and the group of Ruben Martin. He's also done a research stay in the Hartwig group at UC Berkeley, which enabled him to do the work he'll present today. If you like this talk, I'd also encourage you to go back and take a look at the work Craig presented in episode 52. And from there, I'll hand it over to you, Craig. Thank you very much for joining us once again.
Thank you, Matt, for the kind introduction and giving me the opportunity to share my research in a Synthesis Workshop episode. This workshop will cover our recent publication in JACS, where we investigate the mechanism of iron-catalyzed C-sp3H acidation reactions with azidoiodinane reagents, and disclose the features responsible for the high yield and site selectivity. This work was completed while I was a visiting researcher in the Hartwig lab in collaboration with a previous postdoc, Alec Fawcett, who is now working in Cambridge as a postdoc fellow under Matthew Gaunt's supervision. Iron is the most abundant transition metal on Earth, and in part due to its abundance, nature has incorporated iron into many classes of enzymes. One of the most well-studied and important families of enzymes are cytochrome P450, which contain heme as a cofactor. These heme-containing enzymes are able to selectively cleave and functionalize C-sp3H bonds in oxidation reactions. This oxidation is key to oxidizing steroids, fatty acids, and xenobiotics, in addition to assisting in hormone synthesis or breakdown. Beyond the cytochrome P450 enzymes, iron is also essential for the functioning of nitrogenase, hydrogenase, and many other enzymes. Aiming to mimic this reactivity, molecular catalysts containing iron have also been developed, where biological oxidation reactions are within reach, or abiological azidation reactions. Scaffolds for iron-containing oxidation catalysts include metal porphyrin complexes or amine and amidate ligands, while pi-box ligands have been demonstrated to be effective ligands for abiological azidation reactions. Of these iron-catalyzed azidation reactions, the Hartwig lab developed conditions using an iron-2 source and pi-box ligand, along with azidoiodinane, to affect late-stage azidation of C-sp3H bonds. Examples of the method include the derivatization of butylenic acid, which contains multiple C-sp3H bonds, yet is selectively functionalized at a single position. This ability to derivatize CH bonds at a late stage within complex molecules is important for streamlining the synthesis of complex target molecules or creating chemical libraries by derivatization at a late stage. The resulting aliphatic azide can then be transformed into a range of highly valuable CN bond-containing functional groups, such as amines, amides, or tetrazoles. In addition, a particularly attractive application is the use of aliphatic azides in click cycloaddition reactions with alkynes, which allows for both the attachment of fluorescent tags or bioconjugation to biotin. While these studies and those from other researchers have led to valuable azidation methodologies, information about the mechanism of these reactions is limited. A key challenge in understanding these mechanisms is the diverse reactivity by which iron can react, either in one electron or two electron processes, and the paramagnetic nature of many iron complexes. Studies to elucidate key features of the reaction, such as the active hydrogen atom abstractor or azide source, can therefore be used as a blueprint in the development of future preparative methodologies. At the onset of our investigation, we considered several possible mechanisms on the basis of our preliminary mechanistic data, the reported reactivity of azidoiodinane, which is shown as compound 1, and iron-2 complexes. In the first class of mechanism, we considered a radical chain mechanism whereby the iron-2 complex would act as a radical chain initiator. A single electron transfer from iron-2 to azidoiodinane would generate azidyl or iodinane radicals, which can undergo CH hydrogen atom extraction to form a carbon-centered radical. This radical could then react with 1 to deliver the CN bond and regenerate the iodinane radical to propagate the radical chain reaction. In a second class of mechanism, a single electron transfer from iron-2 to compound 1 would form an iodine radical and iron-3 azide complex. the iodine radical could then undergo hydrogen atom extraction of a CH bond to form a carbon standard radical, which could then recombine with an iron-3 azide previously generated to deliver the CN bond. This reforms the iron-2 complex, which would react by another molecule of 1, continuing the cycle. A third class of mechanism could be invoked with iron involved directly in the CH abstraction step. Such a mechanism could look as such where iron-2 reacts with compound 1 to form an iron-3 carboxylate complex. This complex could then react via concerted metallation deprotonation pathway to form an iron alkyl complex, which would then react with 1 to form the desired CN bond and regenerate the iron-3 carboxylate. We envision that these mechanisms, or hybrids of these mechanisms, could be operative, but could be distinguished by investigating the reactivity of reaction components stoichiometrically and during catalysis. We initiated our investigation by synthesizing iron-2 pi box complexes with chlorides and acetate ligands to study their reactivity with compound 1. Both were prepared by reacting pi box with the appropriate iron-2 salts, where the formulation of Fe1 could unambiguously be determined by single crystal X-ray diffraction. We initiated our studies with iron acetate complexes, as those were the complexes used in the standard catalytic conditions, but studied iron chloride complexes later as they were more well-behaved. The stoichiometric reactivity of pi box ligated iron-2 diacetate complex with compound 1 was first investigated in the absence of C-sp3H bonds. Upon reacting equimolar quantities of iron-2 with azidoiodinane, an instantaneous color change to blood red was observed. An analysis of the crude reaction mixture demonstrated only half an equivalent of compound 1 was consumed. The fact that we are not able to detect any other organic products derived from 1 by proton NMR suggested that both azidyl and iodanyl units of 1 are transferred to iron. Analyzing the reaction mixture by paramagnetic NMR, UV-Vis, IR, and EPR spectroscopy, along with MALDI mass spectrometry, we're able to identify the fate of iron speciation. From these techniques, we observe the complete conversion of the starting iron diacetate complex and oxidation to iron-3, where we identify the formation of an iron-3 azide complex and presumably an iron-3 carboxylate complex. To study the electron transfer reaction between iron-2 and azidoiodinane in more detail, we performed cyclic photometry studies which revealed the redox properties of these compounds and their possibility to react during catalysis. The cyclic voltammogram of compound 1, the green trace, displayed an irreversible reduction at minus 0.43 volts versus SCE, while the iron pi box complex displayed a reversible reduction at minus 0.045 volts versus SCE. To assess if the iron complex could reduce compound 1, we added 2 equivalents of azidoiodinane to a solution of pi box ligated iron-3 trichloride. Scanning in the negative potential, we observe a significant increase in currents in the iron-3 to iron-2 reduction, in the absence of return oxidation peak, which was previously reversible. This is consistent with an iron-2 species reducing compound 1 and forming an iron-3 complex. While thus far we provided strong evidence that iron-2 reacts with azidoiodinane to form iron-3 species, the iron acetate complexes displayed high functionality, which were difficult to study. As such, we studied less dynamic iron chloride complexes. Consistent with our previous experiments, reacting pi box ligated iron dichloride with azidoiodinane resulted in an instantaneous color change to dark red. Comparing the EPR and UV-Vis spectra of this reaction mixture to an independently synthesized iron-3 azide complex saw strong overlap in these spectra. The G values from the EPR spectra were 4.35 and 2.03, which supports an iron complex with a spin of 5/2 and an octahedral geometry. The paramagnetic NMR spectra from the crude reaction mixture in pi box ligated iron-3 azide complex also overlaid well. Together, these findings provide strong and consistent evidence that an iron-3 azide is generated upon reaction with iron-2. With this independently synthesized complex in hand, we studied its reactivity under stoichiometric settings with C-sp3H bonds and AIBN. While no reaction is observed between the model substrate isopentylbenzoate and the iron-3 azide complex, The reaction with AIBN, a source of alkyl radical, delivered the alkyl azide in a 50% yield. These findings are consistent with the iron 3 azide not being involved in CsP3H cleavage, but can react with free alkyl radicals to form carbon azide bonds. With these experiments in hand, we assess the ability of azidoiodinane to undergo homolysis to form azidyl radicals and iodanyl radicals. Under the standard catalytic conditions, by replacing the alkane with Z or E stilbene, the diazide 11 was obtained in 59 to 64% yield. Without the iron 2 catalyst, however, Z stilbene isomerized to E stilbene. This result is in agreement with homolysis of the IN bond occurring under the standard reaction conditions without iron. However, an azide source that is not compound 1 is required to trap the benzylic radical generated upon azide addition into the olefin. This interpretation was further supported by adding in radical trapping reagent TEMPO, which forms the oxyazide product with or without iron 2 catalyst, as TEMPO reacts rapidly with the alkyl azide formed. These findings support the reversible generation of azide radical addition into stilbene, which reverts back to the stilbene without a reagent that is capable of trapping the benzylic radical. Probing the reversibility of homolysis and the effect of solvent choice on the reaction outcome, the thermolysis of compound 1 was performed in acetonitrile or DMSO. In acetonitrile, mainly recovered starting material was observed, while in DMSO, a solvent in 1 is much more soluble, significantly more of 1 reacted to form compounds 5 and 4. These thermolysis experiments support that compound 1 reversibly undergoes homolysis under the reaction conditions, as most of 1 is not consumed. To obtain more information about the species involved in the catalytic reaction, we studied the azidation of trans and cis declin in iron-catalyzed and uncatalyzed azidation reactions. Performing the standard reaction of trans or cis declin formed the same ratios of cis and trans azidation products of a 4.5 to 1 ratio. These results indicate that both isomers proceed by intermediates 6A and intermediate 6B. Repeating the same reaction but without an iron catalyst, the tertiary azide products were formed in a 2.2 to 1 ratio, and unreacted cis-declin had undergone nearly full isomerization to trans-declin at the end of the reaction. This isomerization provided further evidence for the formation of radical intermediates, and that CH cleavage is reversible in the iron-free conditions and irreversible in the iron-catalyzed conditions, as isomerization is not observed. The difference in DR between the iron-catalyzed and uncatalyzed reactions also provides support for different azide transfer reagent. In the iron-catalyzed reaction, an iron 3 azide would transfer the azide group to an alkyl radical, while in the iron-free conditions, compound 1 would transfer the azide. To distinguish between if iron is serving as an initiator or is involved in a closed iron 2 iron 3 cycle, the ratio of isomeric azide products were monitored as a function of time. Monitoring this reaction, we observe a consistent 4.5 to 1 ratio of cis and trans azide products, which is consistent with the iron azide being regenerated during catalysis. If the iron 2 complex only serves as initiator for radical chain reaction, then only one equivalent of product per iron complex would be formed at a high cis-trans ratio, and then gradually approach the 2.2 to 1 ratio of the iron-free conditions. Conducting the same experiment, but without iron catalyst, we observe that a 2.2 to 1 ratio is maintained. Additionally, comparing the rates of reaction between the uncatalyzed and iron-catalyzed reactions, the iron-catalyzed reactions proceed at around 7 times faster than the uncatalyzed reaction, suggesting it increases the rate of radical trapping and the overall reaction. More details on the kinetics of the reaction are provided in the later section. Thus far, we have demonstrated that the iron complex is unable to abstract a CH bond and that homolysis of azidoiodinane occurs under the reaction conditions to form azidyl and iodanyl radicals. We therefore aim at identifying the species that abstracts the hydrogen atom from the CH bond. Quantifying the products from catalysis, we identified that benzoic acid is formed as a major product derived from the fluorinated compound 8. While the formation of benzoic acid is consistent with iodinane radicals abstracting the CH bond from the alkane, we sought to provide more direct experimental evidence that iodanyl radicals are involved in hydrogen atom extraction. As such, a set of electronically differentiated azidoiodinanes were synthesized, and their effect on selectivity was determined. If the electronic properties of these reagents influence regioselectivity, then the iodanyl radical is one of or exclusively the species that undergoes hydrogen atom extraction. If the electronic properties do not influence regioselectivity, then the iodanyl radical is likely not involved in hydrogen atom extraction, and the azidyl radicals are likely the radical that abstracts the CH bond. To probe if modifying the electronic properties of azidoidenane affected site selectivity, the azidation of biphenyl compound 17, which contains two electronically similar but sterically distinct benzylic CH bonds, was conducted, and the ratios of secondary to tertiary functionalization was compared. The measurable difference between these values demonstrates the electronic properties of the arene backbone has an effect on site selectivity and is consistent with hydrogen atom extraction from the iodinane radicals. To enable the information obtained in the previous sections to be assembled into a complete mechanistic picture, kinetics of the catalytic process were studied. Initial rates of the azidation were performed and found that the reaction was first order in alkane and first order in azidoidenane. The reaction was also found to be zero order in iron-catalyzed. These reaction orders are consistent with rate-limiting CH cleavage, in that the generation of radicals involved in hydrogen atom extraction are derived from the homolysis of compound 1. The greater rate of reaction in the iron-catalyzed azidation versus the iron-free azidation is therefore due to the reversibility of hydrogen atom extraction, from reversible in the absence of iron to irreversible in the presence of iron. Performing the standard catalytic reaction with pibox-ligated iron dichloride complex and analyzing the reaction mixture at 30 minutes, we're able to identify if iron azides were present during the catalytic reaction. Comparison of UV-Vis, paramagnetic NMR, and EPR spectra of the catalytic reaction mixture to the previously isolated iron-3 azide matched well. Mass fragments from the iron-3 azide could be identified by MALDI mass spectrometry, which together support that an iron azide was a resting state during catalysis. The effect of faster radical trapping on the success of CH azidation is shown with examples here. Substrates containing alpha-cyclobutyl groups were able to undergo azidation without ring opening under the standard reaction conditions, while the same reactions without an iron catalyst led to complete decomposition. This is attributed to the rapid trapping of the alpha-cyclobutyl radical with an iron-3 azide, which outcompetes ring opening. Beyond this specific motif, all substrates compared in iron-catalyzed versus uncatalyzed azidation reactions perform better, highlighting the importance of limiting the lifetime of alkyl radicals by trapping with an iron-azide complex. To summarize, the reaction between iron-2 and azidoidenane forms equimolar quantities of iron azide and iron carboxylate. These complexes do not abstract CH bonds from the substrate, but instead azidoidenane undergoes spontaneous homolysis at 50 degrees Celsius to form iodinane and azidyl radicals. These radicals can then undergo rate-limiting hydrogen atom extraction from the weakest CH bond of the alkane to form an alkyl radical. The alkyl radical generated then recombines with a resting state iron-3 azide due to the strong polarity match between nucleophilic alkyl radical and electrophilic iron azide, and forms the CN bond. Together, these experiments delineate critical features of the iron-catalyzed and uncatalyzed azidation reactions, and describe features responsible for the higher yield and broad scope of the iron-catalyzed reaction. Lastly, I'd like to thank John Hartwig for hosting me and his research group as a visiting researcher, and the lab members at Berkeley for great times. I'd like to thank my supervisor, Ruben Martin, for giving me the opportunity to do research abroad, and the BIST and European Union for helping fund this work. If you have any questions about the work or my time at Berkeley, you can contact me on LinkedIn or by email. Thank you for your attention, and I hope you enjoyed the presentation. Have a great day.
Thank you for joining us for this Research Spotlight episode, and thank you to Craig for another great talk. If you enjoyed the episode, you can support us by subscribing and telling your peers about this podcast, and feel free to send us any questions or comments you have. Follow us on Twitter to stay up to date, and see you all next time.